We have the last little bit here of naming to sort of finish, and then we will be done with it, hopefully. So last time we talked about really sort of type 2, type 3 compounds, which are nonmetals and nonmetals together, basically two nonmetals. Remember that these are the types that you really do use prefixes for. So, the nice thing about these guys, as we talked about, are that they are pretty much pretty simple to do. You pretty much just need to count what's there. You don't have to worry about, charges or balancing it out to zero or anything like that. There are a couple of things that we don't do. Again, a reminder that mono is not used on the first name, but it is okay on the second. And the other sort of major thing that occurs with type 3 is we sometimes get a couple of vowels that back up to each other, one from the prefix, one from the element. And in the case of like an A and an O or an O and an O, we typically will get rid of the vowel that comes from the prefix there. Other than that, it's basically the appropriate prefix if needed, and the whole name of the first metal, or the first element, I guess, better way to say that, and prefix, and the second guy gets the normal non-metal treatment where it ends in IDE. So again, these are pretty straightforward. Write prefix and write it down. We finished up, I think, talking about polyatomic ions. Polyatomic ions are kind of interesting things. They really are groups of nonmetals together that are really held together by sharing of electrons, but they do have an overall charge as a result of sort of the sharing of electrons that occurs. For example, I think we looked at NH4, NO3. Those again are two polyatomic ions. And from drawing the Lewis structures, as we talked about, really NH4 plus is this guy here. Our nitrogen is sharing electrons there with the hydrogen. The end result, though, is because of all the sharing of the electrons, it has an overall sort of positive charge. So it's still considered an ion, even though it really is something that's sort of sharing electrons. And nitrate, for example, as we also, I think, drew the other day, looks something like this. Also, that nitrogen and those oxygens are sharing those electrons, but does end up with an overall -1 charge. So even though they really are sort of covalent compounds, they do end up with this sort of overall charge. So they're really treated like ions. And as an ionic compound, that is again why ultimately, even though there's a lot of letters and elements happening there, we're ultimately still putting something that is +1 together with something that is -1 together, which is why when we look at the formula here, we do end up with just one of each that is needed. Because most of the polyatomic ions, as we talked about, pretty much will be negatively charged, they very commonly are found with metals. And what that means is, as we talked about, what we want to do is basically kind of roll back to our type 1 and type 2 sort of rules for naming. And again, that involves the metals. And obviously, if it is a type 1 compound, it has a fixed charge, which basically means you don't need to worry about any Roman numerals or anything like that. And we would just use the whole name of the metal and also the whole name of the polyatomic ion. If it is a type 2 metal, then just like we did with type 2 compounds, you need to figure out what the charge is on the metal. You do need to include a Roman numeral to indicate the charge on the metal. And we still, again, just use the whole name for the polyatomic ion. So, like FeNO3, 2. This is iron, which is a type 2 metal. Again, as we can see above, nitrate right here is -1, and there's 2 of them, which means in this case, the iron would be carrying a +2 charge. And because it really is a type 2 metal, we would need iron Roman numeral 2. And again, nitrate, the whole name here of our polyatomic ion, just like with type 1 and type 2, even if you have more than one polyatomic ion, it has no effect on the name. So we just simply use nitrate. Again, we would not use any type of prefixes here with it or anything like that. A vast majority of the polyatomic ions, as we talked about, basically end in ate or ite, and you could kind of group them together. There's kind of groups of 2 and kind of groups of 4 that are related to each other. The only difference between the members of these sort of groups are the number of oxygens that are involved. They all have kind of the same charge, just the different numbers of oxygen. So like our nitrate, which is NO3 minus, and our nitrite, which is NO2 minus, they both have a -1 charge. And again, the only difference is the number of oxygens. The one with the least typically will end in ITE at the end. The one with the most will end in ATE. There's also groups of 4 that are related. So we looked at perchlorate, chlorate, chlorite, and hypochlorite. And in that sort of group of 4, basically, you split them off into 2s. The 2 with the least number of oxygens will end in ite, and the one with the least oxygens out of all of them will start in hypo. So that's how we get the hypochlorite. And the 2 that have the most oxygens will end in ate, and the one with the most oxygens altogether will get the per in front of it. So, those are the ones you could sort of remember as well. The best way to do it, and like I said, sometimes people will just remember perhaps all the 8s and know, again, the ites should be pretty much the exact same formula, just 1 oxygen less. So that's an easier way maybe to remember it. Or you could do all the ites and then know that if you needed an 8, it would be 1 oxygen more. So that's some ways sometimes people will do it. Other things that we commonly saw as well on that sort of table is occasionally we will put H plus in front of something, and that basically is added to the name. So like HCO3, which is basically off of carbonate, which is CO3 2 minus. That is known as hydrogen carbonate, also known as bicarbonate as well. The last thing is, obviously, as we see here in this formula, as we talked about, if you are in a situation where you're writing a formula that includes more than 1 polyatomic ion, you do need to put parentheses around the polyatomic ion and the number on the bottom right as to how many that you have. Any questions on that stuff that we talked about last time? Okay, so last couple of things in terms of naming we're going to talk about. The first one is we're going to talk about how you name acids. So let's first talk a little bit about acids. Acids are really a substance that has the ability to form H plus or hydrogen ions in solution. So something that, when it basically goes for a swim, will break apart and produce some H plus, which is known as a proton, or hydrogen ions in solution, free H plus floating around. And that is your basic definition really of an acid. While we're at it, a base, on the other hand, is something that can produce hydroxide ions in solution, which is one of those polyatomic ions. And that's your basic definition of a base, is the ability really to produce OH minus in solution. The good news about bases are they're named like normal sort of polyatomic ions. So if you had NaOH, it would be sodium hydroxide. So they're just kind of named normally. Acids are named a little bit different. And it really all revolves around whether or not the acid contains oxygen. So if the acid contains oxygen, we name it one way. If it does not contain oxygen, we name it another way. And so, for example, let's take a look at that here. So really, if we are dealing with acids, it's really about, does it have oxygen? And pretty easily here, if the answer is no oxygen, the acid name will start with hydro something ic acid. So hydro something ic acid. What makes something an acid, by the way, is that H plus, which means the cation in all acids are H plus. So the cation is always H plus. The positive guy is always at H plus, which makes it an acid. So if we had something like HCl, and this is an acid, it has no oxygen. So we would start with hydro. The middle part that's missing comes from our negative guy here, and that would be hydrochloric acid in this case. If we had HBr, again, looking at this, no oxygen. So we'll start with hydro. The negative guy here is bromine. So that would be hydrobromic acid. If I had H2S here, what would this acid name be? Yeah, it would be hydrosulfuric acid. Again, no oxygen involved, so it starts as hydro, and it would be hydrosulfuric acid. Now, again, because the cation here is H plus, the anion in the first one is Cl minus. From the second one, the cation is H plus, and the anion is Br minus. Now, the third one, the cation is still H plus, but there's not one of them, there are two of them. And the reason there are two is because the anion is sulfide, which is a -2 charge. So it really is, acids are treated like ionic compounds, even though it really does contain two nonmetals and stuff like that, but they are treated like an ionic compound here. And we do want to kind of balance out the charge where the cation is H plus. Any questions on that? Now, if you remember earlier on when we were talking about, I think we're around there, type 3, we talked about hydrogen and kind of some unusual ways we sort of name hydrogen. And if we have HCl like this, and it is, say, a gas, we would call this hydrogen chloride. So what is the difference between HCl that's a gas and HCl that is AQ? AQ means aqueous. It means it's a solution. It's swimming around, basically, yeah, in a water environment. So that is why most acids will always have the AQ symbol next to it to indicate that it is an acid. Otherwise, if you had HCl that had the G next to it, it would just be called hydrogen chloride gas. You actually take hydrogen chloride gas and bubble it through water and you get hydrochloric acid. Basically, it basically gets hydrated with all the water ions that are molecules that are in there, and it makes hydrochloric acid. So AQ means aqueous. It basically is a solution. It's a water environment. And all acids typically will have that AQ symbol next to them to, again, indicate that you are dealing with an acid. And technically speaking, when you write the formulas for acids, you should also include the AQ symbol next to it to indicate that it is an acid and not something else. Any questions on acids with no oxygen? So those are the guys with hydro. Now, let's talk about then if the answer to our oxygen is yes. So if your acid does contain oxygen, it is what is sometimes referred to as an oxyacid because it contains oxygen. It also will contain everybody's favorite thing. It will contain a polyatomic ion. So most oxyacids will contain a polyatomic ion that we talked about there a second ago. And as we just talked about, pretty much our polyatomic ions will end in one of two ways, ate or ite, right? So if your acid does have oxygen and your polyatomic ion ends in ate, your acid will be something ic acid. So absolutely no hydro here because hydro is just for guys that do not have oxygen. So if we had HNO3, this is NO3, which is a polyatomic ion of NO3 minus, which is nitrate. So this would become nitric acid. H2SO4. SO4 is SO4 2 minus, which is sulfate. So this would be sulfuric acid. About H2CO3, what would that be called? CO3 is CO3 2 minus, which is carbonate. So this would be carbonic acid. Any questions on those there? Now, if your polyatomic ion in your acid ends in ITE, the way that we name it is same deal. We kind of start with the front part and it ends with OUS acid. So something OUS acid. So if we take HNO2, NO2 is NO2 minus, which is nitrite. This becomes nitrous acid. H2SO3. SO3 2 minus is sulfite. This will become sulfurous acid. Again, no hydro in this as it does contain oxygen. So with acids, people make a very common mistake is they want to like throw hydro in everything because it kind of sounds right. But hydro is specifically only for acids that do not have oxygen. And if it does have oxygen, you should not be putting hydro in it probably at all. And again, those guys with oxygens, it's really that polyatomic ion which determines how you go about naming them. Same thing if you want to look at the cation or anion here. For example, for our nitric acid here, cation is H plus. The anion is nitrate, NO3 minus, again, -1, +1, which is why we just need one of each of those. Any questions on that there? Yeah. It's based on the polyatomic ion that's present. So it will go back to like when we were talking about polyatomic ion, that list, you gotta have to know that list. And that once you know, when you look at something like NO3 minus is nitrate, that will help you do the acid part of it. Yeah. So in terms of oxyacids, they really are tied to that polyatomic ion list. So it's really important to understand the names of those guys and the formulas as well. So it'll help you balance it out. Other questions? All right, so as I mentioned before, as we just did there, no oxygen. We got the hydro and the ick at the end. And obviously, we use the negative guy there to fill in the missing part. So here's some acids. Let's take a look at some here, I think. I got here. All right, so I did some of these. So why don't we switch these up here? Let's do HClO4. Let's do HI. Let's do H3PO4. And then let's do all right, so names and then some formulas there. Okay, let's take a look. So starting with the first one, we have HF. So we do not see oxygen. So that means it should start with hydro. Ick acid, the middle part will be filled by the negative guy here, which is fluoride. So this would be hydrofluoric acid. Coming down below it, we do see oxygen. So we know it should be a polyatomic ion, which would be this guy right here. That is ClO4 minus, which is perchlorate. And since it ends in ATE, the acid should end in ic. So this would then become perchloric acid. Again, no hydro on this one because it contains oxygen, but we do keep the normal name there, part of it, the per part of it from perchlorate as we go through it. Any questions on those two? HI, no oxygen here. So this is going to start with hydro, something ic acid, the middle part being the iodide. So this would be hydroiodic. Oops, extra I there. Trying to squeeze it in. Iodic acid in this case. Any question on that one? Coming here, we do see oxygen, so we want to really isolate our polyatomic ion, which is PO4. Again, from our polyatomic ion list, that is PO4 3-, which is why there are 3 hydrogens, right? Each at +1 balances it out. That is phosphate, which means this should be phosphoric acid. Any questions on that one in there? Looks very similar right below it. We again see oxygen, so we want to isolate this. So this is PO3 3-. Come here. By the way, I know it's 3- again because there are 3 H's there, right? Which gives us +3, so this has to be -3. So let's just say in this situation, you're not really sure what this is named, but you do know that that is phosphate. They are related to each other. The difference is the guy on the right has 1 less oxygen, which means instead of phosphate, it's probably called phosphite, right? Which means that our acid name would then be phosphorus acid. Any questions on that one there? All right. So that is obviously formulas to names. If we're going from names to formulas, you want to look at the name and get the information out of it that will help you do it. What we do know is the cation or the positive guy is going to be H+. So we really just need to figure out for acids what the negative part is. I see chloric acid. That means I do not see hydro in the name, which tells me it does contain oxygen in this case. And because it contains oxygen, I also know that it should contain a polyatomic ion. And I see that the acid here ends in ic, which means my polyatomic ion should end in 8. And you literally could just get rid of the ic and put 8, and you see chlorate there. And that would be the negative guy that would be part of it. Chlorate is ClO3-. So +1 and -1 would give us a form of HClO3 with the aqueous symbol next to it, would be chloric acid. So you could kind of rebuild the negative guy's name from the acid name, and that will hopefully give you the correct formula that you need. Any questions on that there? This is hypobromous acid. Does not contain hydro, even though it says hypo. This is not hydro. So no hydro means, again, it contains oxygen, which means it again contains a polyatomic ion. So it does end in OUS, which means my polyatomic ion would end in ITE in this case. So again, you can literally just take that out and put ITE at the end of it, and it is hypobromite. Now you may say to yourself, I don't know what hypobromite is, but we did see one in a group of 4 that was called hypochlorite. Yes, and hypochlorite is ClO-. So what would hypobromite be? BRO-. Bromite, bromine, right? So instead of chlorine, remember that one you can switch out with anybody in group 7. So bromate, bromite, you can switch it out, which means that this negative guy here would be BRO-, which means our acid would be HBRO, and that would be hypobromous acid. So if you have the acid name, you could kind of, like I said, kind of rebuild the name of the negative guy, and again, get that correct formula. And really the positive guy with all acids, H+. So just got to put it together to equal 0, and you'll have the right formula. Any questions on naming acids? All right, so let's get this here real quick. One last thing I do want to talk about was we'll kind of relate to lab. So since we're getting to the end, why don't we talk about it? And that is hydrates. And hydrates are really two parts. There is a salt part, and there is basically a water part, which is what is referred to as the hydrate part of it. And a salt is an ionic compound. And obviously water is H2O. So hydrates have really weird sort of looking formulas, and they have this little dot that typically becomes from in between the salt part and the water part. So if we had something like CaSO4 dot 5H2O, this is the salt part. That is obviously the water part. And again, it is like a little dot that they put between those formulas. How do we go about naming it? Is we simply name the salt like we would normally. The guy here, that is a metal, that's a polyatomic ion. So that is calcium sulfate. And then we actually use prefixes for our waters. So mono, di, tri, penta here for 5. Kind of similar prefixes that we use in type 3. And then for the water, we just simply call it hydrate. So this would be calcium sulfate pentahydrate. Actually we'll do. This we would look at it, which would be the salt part. That is iron, which does need a Roman numeral. So iron here would be based on what we have here, which is SO4 2 minus. That's going to be a +2 for the iron. And we would call this iron Roman numeral 2 sulfate. The prefix for 7 is hepta. And this would be, I'm running out of room, I'll go underneath it, heptahydrate. So hydrates have some unusual little formulas with a little dot in between. We're not necessarily multiplying anything here, but the dot basically means that the iron sulfate basically has 7 waters basically surrounding it. And sometimes people are also confused like this, like today in lab, the hydrate is actually a solid. So as the solid crystallizes, it actually crystallizes some water with it around it, and they're all really a solid at this point. Now, when we take something like this, which is a hydrate, like we're going to do in lab, and we heat it, right? So if we took something like our calcium sulfate here and our 5 waters, and we heat it, what's going to happen is we're basically going to evaporate off the water part of it, and we will end up with calcium plus 5 waters that come off. And that's essentially what we're going to do here in lab today, is heat this. This is what is known as the hydrate. This is what is known as the anhydrate, which means it lacks water. And what we're going to do in lab today is basically heat it up. Water will come off. The difference in the mass of the hydrate we started with and what we're left with at the end will give us how much water came off, and we can calculate what we want to do there, which is, I think, the percentage of water that was basically in our hydrate by the mass of water that was lost divided by the mass of the hydrate. So hydrates, again, you name really the salt part, the front part of it, like type 1 or type 2. And the second part is hydrate at the end with the appropriate prefix for how many waters that you have. Any questions on naming hydrates there? All right, that wraps up this chapter. That also wraps up, again, everything that is on our exam, which is 1 week from today. Yes. So our exam is 1 week from today. It covers chapter 5, it covers 12, 11, and I think there's one more in there. I don't remember at this point, but one more is in there, I think. And so that's like some electron configuration, that's bonding, that's naming. And like I said, I think there's one before that somewhere that we did as well. That is Wednesday of next week, followed by spring break after that. Yes.